today. Lowest common ancestor of deepest leaves. Given the root of a binary tree, return the lowest common ancestor of its deepest leaves. Recall that the node of the binary tree is a leaf, if and only if there has no children. The depth of the root of the tree is the root of the tree is 0. The depth of the node D is the depth of each of its children D plus 1. The lowest common ancestor S of a set S of nodes is the node A with the largest depth, such that every node S in the subtree with root A. Alright. Find the lowest common ancestor of its deepest leaves. The lowest common ancestor. So if there's more than one, so if there's only one leaf, then it's just the parent of it, I guess. So like here, and there's 2 leaves that's the lowest, so it has to be this one. But if only if the 7 and 4 were eliminated, then the deepest leaves would be all 4 of these, and the common ancestor would be 3. Okay, sure. Alright, so it's been a while since I did something like this. How to approach this? I think what would make sense is try to find the leaves first, the deepest leaves first. Can I logic my way about this? So if you have one deepest leaf, then it's just the parent. And if you have multiple deepest leaves, is it true that it's going to be some number of, so if you have 2 deepest leaves, let's say the deepest leaves were just the 6 and the 8, then the lowest common ancestor would be the 3. Lowest common ancestor. So yeah, I think I need to know what the deepest leaf is, and then just find the common ancestors. And then determine deepest leaves. So I think here we'll have a depth first search, which will require DFS. No, it's breadth first search. Breadth is like taking levels at a time. Depth is taking like all the way down. Breadth first search to determine to find leaves, which will require using like a deck, double-ended queue. So for a deck, what we want is an array that starts with the first node, which is going to be the root. And while we process the deck, how does it go? While deck is true, I think what we do is so while there's a deck, what we'll do is we'll go through each level at a time and add onto the double-ended queue the children of the current level. So current level size is the length of the deck, and then for each node in this deck currently. So for index for I in range, it's not really index, for I in range of the current level size, we're gonna take the top off. So node equals deck dot pop left, and a double-ended queue is you can take it from either end. So we're going to take off from the top the last thing added, and then we're going to add all the children of it. So for if node.left, so if it has the left side child, then add that node, deck.append node.left, and then if node.right, deck.append node.right. Now how do you tell that there is no child? Or how do you tell that there's going to be leaves? So a leaf would be I think you can tell if there's a leaf maybe by so if the current level is, so like the deck is initially 3 and then it puts onto the stack, onto the deck 5 and 1, and then while popping off the 3, and then when it processes 5 it puts on 6 and 2, process 1 puts on 0 and 8, so it'll be 6, 2, 0, 8. And then when it does 6 it doesn't do anything, 2 adds on 7, 4, 0 doesn't do anything. So the deck is going to be empty here. Deck is going to be empty here. So I guess if you know that, let's say we have let's say we just have a leaf set, and it's going to be reset each time. For each level, for each level there's just a leaf set. If node.left, if there is no left child and right child, then leaves. I mean, logic seems unnecessary. There should be some way, because it's pretty much the last level that you would have as pretty much the last level that you would have as the leaves if there wasn't anything added onto the deck. So is there a way to just keep the last level? If there's no way, alright, I think maybe last level is just a stack, or just a list, and I'll just say if node.left append, and then we'll say last level append this node, and then if there is now it needs to be inside here. So the last level should be the leaves. Should be leaves at this point. And I'll just print out the last level just to make sure it's working. Node dot. I think this should be deck is your root. Oh, oops. Deck starts out with the root. Alright, and the last level is 7-4, that's correct. Last level should just be 1, and last level should be... So here, the deepest node is 2. The deepest, so 0 goes to 1, 3, 1 goes to 2. Okay, interesting. If you have just one node, then it's the lowest common ancestor of all leaves. And the last, okay, 2. Okay. So now we just need to find the lowest common ancestor of everything inside the last level list here. So is there a quick way of determining that? So when you have, because the last level could be multiple. It's not really based on, it's not really based on, how did you find the lowest common ancestor? What was the general algorithm there? Lowest common ancestor, it's like generally a recursive function, or not recursive, like a kind of a, you define another function that goes through the nodes. I guess it's recursive, yeah. 7 for the lowest common ancestor of basically a set of nodes, but technically the nodes are all at the same level. So you could, so for each node in the set, so the set here could be 7, 4, you go to the parent, you create a, for each node of the set, you just add the parent of that node until basically you're down to one parent. I think that works. Okay, so I guess this requires another deck. Yeah, I think this requires another deck. So let's say you go through your last level with your leaves, and what we're going to do here is we're going to, for each node, add, oh wait, I don't know the parent of the node. The node only has its the node only has its left and right. I mean, I could append that information to the nodes. It's not that much information. Yeah, what if I tried that? I'm not sure how much more memory that would take. So node dot left dot think you can just do this. Equals this node and node dot right dot parent equals this node. I need to go and print out the last level again to see if this added that information. I think maybe I need to redefine the node class if I want to do this. Yeah. Yeah. So not like that. So for each node, add its parent. Alright, I guess I can just do a dictionary. Parents will be a dictionary. And I'll say parents of node.left equals this node. Parents of node.right equals this node. I wonder if I should just do the node.left.value. Let's go ahead and just print out that. No, I think I need the reference to the node. Yeah, so parents, the parent of the node 5 should be node 3. Parent of node 5, which is this node, left, right. Alright, just to make this easier on myself, I'm just going to do right now node.left.value, node.value. I do need the actual reference to the node rather than the value of the node, but just to make sure that this is working as intended. Okay, the parent of node 5 is node 3, 1 is 3. Okay, excellent. So, going back to actually storing the nodes themselves, because we need to process it again. For each leaf of a step, while the length of the last level, while the length of this deck is greater than 1. If it's 1, then it's the common ancestor. What I'm going to do is, maybe this should be a set. Maybe this should be a set. Actually, yeah, the last level last level append it, and then go through all the elements of the set. Let's go set. While the length of this set is greater than 1. Oops. That's not how I want it. Let's go nodes is the set created from the last level of leaves, while the length of these nodes is greater than 1. And then I'll say P is equal to P nodes is parent nodes. P nodes is another set, and while and for each element in the current node set, P nodes dot append the parent of this node. And I think no, P nodes is going to add, not append. And then lastly, once I do that, I now make the current nodes equals to the P nodes. And then I return, how do you return any element in a set, like nodes of 0? I don't think I can, how to return single element of set. Is it set.last? Pop. It's going to return a tree node, so nodes.pop. Nodes is the set unhashable type. Oops, I think it's just the set that is the last level. Okay. Okay, I think that works. See if how it compares. Probably too slow. Okay. So how much memory did other people use? Marginally less. So you have a deck, and you go through each depth, and you add the current depth to the deck. I wonder if I should just use a two sets, where the sets are just use two sets where the sets are each level, and like this thing kind of alternate between them. So let's say I have a level set, and that's going to start with just the node. I think that's how you do a single set. I think it's with the curly braces. Okay, so the level is this one. So while there is something in the current level, we'll say the next level is an empty set. and then you iterate through for each index and for each node in the current level. And then the next level is going to append the left side and right side of that node. So next level or add. And next level dot add node dot right. And then you keep track of the parents of these nodes. At that point, when you're done, your last level, no, after you're done here, you're gonna say your nodes should be your next level. You need to reset it. So your next level becomes your level. Yeah, so you create a new set for your next level, and then, okay, at this point, level should be keeping track of the last thing. No, whoops. No, at this point, level becomes next level. But then you lost then you would lose track if you said level equals next level here. Like you want to keep your old level at that point. So maybe I'd make this a while true loop. And I make this be where the condition is checked. So if the length of next level is 0, then break, otherwise it'll reset it. Alright, at this point level should have your last nodes. Like that. Okay, level is the set that includes the first, oh whoops, not node. Level has the root. Okay, 7, 4 is the last level, 1 and 2. Okay. So I don't, so I can just say leave the nodes I'm dealing with are from the level I just finished. Okay. Maybe this is split master. Alright. A little faster. A little less memory. So you have a level and then you create a next level. And you create a dictionary for mapping nodes back to their parents. I wonder. The number of nodes in the tree will be in the range 1 to 1,000. Values in the nodes are unique. So I wonder, can you you need to figure out which are the end nodes, right? So you so I mean you could do something that is not a dictionary like this. You could do an array where the array is 1,000 long. I mean, does that help at all? So, and then instead of storing nodes, you store just the values. So 1,000 parents of the buff value, and then technically at that point you need to be dealing with values instead of nodes. So when you create the leaves, instead of creating the set of nodes, you want to create the set of node values. So nodes is a set created from a list of val for each node.val for each node in level. Did not work. So let's go ahead and just print out maybe what this is doing. Just coming up with the right answer here. Oh, it's not going to work because when I do nodes.pop, I want the actual node of the last value, not the number. So it's giving me 2, which is the node value. Parents. So no, I guess I could do an array here where the index in the array is the value, but the actual information stored is the node. Okay, so the array has nodes at certain indices, and then when you set of the nodes at this level, and then while there's more than one node, you're adding the parents of the current node's value as the index. Okay. Nodes is the set from the current level. Alright, does that help at all? Oh, sweet Jesus. Okay, so the difference there was just going from an array to, or from a dictionary to an array, a fixed size array. Okay, I guess this is pretty clean. So you have your root node. You create a set with just that node. You have a mapping of children to their parents, which you store as an index for the child, mapping to the actual node for the parents. This is mapping from child value to parent node. And that's more efficient than, or this is going to be quicker than using a dictionary, because it's like numerical indexing is faster than hash indexing. And then you create the set of nodes, track children of current level. Children of nodes of current level. And then for each node in the current level, basically the parents, if there's a left child, add it to the next level, make the connection between that child and that parent. And then same for the right side. If there is no children of the current level, then break current level is all leaves. Otherwise, move on to the next level by changing the current level to be the next level. And then go through the nodes again, but this time using a set. Oh, wait, level here was a set, no? Oh, this is stupid. Yeah, this is just going backwards. So I say, while there are nodes of this level, let's say the parents of this level is another set, and for each node in this current level, then the parent level will be adding the parents using the node's value, and then the P level, the level becomes the parent level. And the parent level is 1, that means it's the common ancestor. Let's just clean that up. No, if the current level after all that is done. What? How is this slower? How is this much slower? There's no way. Is this just random timing? Sometimes it's 0, sometimes it's 100. Oh my god. It's just random timings. Okay. Alright, whatever. Summary. This is identify or use breadth first search to go through each level of tree. Here we're going to use basically an alternating set method. I only use a deck, but here I want to keep track because like the very last set, so I use an alternating set. I think there were probably other ways of doing this as well, but whatever. Use an alternating set method to keep memory of the last level leaves, and then also use a dictionary or array mapping to keep track of children to their parents. After identifying children, go through levels, go through and do alternating sets backwards, basically add child nodes parents to a set. And when only one parent remains, then that is common ancestor. Alright, time complexity here. This should be O of the number of nodes. You go through pretty much every node as you go downwards. It's not possible to just ignore a node. And you only go through it once as you go downwards, and then you go through and you go to at most O of n to go upwards, like in the worst case, like your common ancestor is your first root. And then space complexity, here it was also, well, I used the parent mapping, so, and then I also use sets. Yeah, it's like O of n, the sets, and O of your values for the array mapping, because I know that the values in the array are between 1 and 1000, but otherwise, or could have used could have used a dictionary to track mapping, to track child parent mapping for O of n instead.